Intermittent fasting, IF, a dietary approach that cycles between periods of eating and fasting, has drawn increasing attention for its potential to influence brain health at the cellular and metabolic levels. Beyond weight management and blood sugar control, IF may directly impact how the brain processes, stores, and utilizes sugar, particularly through its effects on glycogen turnover, insulin sensitivity, and energy stress pathways. By intermittently depriving the body of dietary glucose, it forces a metabolic shift that could help reset dysfunctional sugar metabolism in the brain and possibly halt or reverse early signs of neurodegeneration. During the early stages of fasting, the body consumes circulating glucose and then begins to draw on liver glycogen stores to maintain blood sugar levels. Eventually, as glycogen depletes, cells adapt by increasing fatty acid oxidation and producing ketone bodies, such as beta-hydroxybutyrate, which the brain readily uses as an alternative fuel. This transition away from a glucose-dominant state toward metabolic flexibility is central to the concept of a brain energy reset. In the context of modern diets high in refined carbohydrates and frequent eating windows, the brain is often exposed to chronic glucose availability, potentially contributing to insulin resistance, impaired glycogen turnover in astrocytes, and buildup of toxic metabolic byproducts like advanced glycation end products, AGEs. If introduces a break in this cycle, one of the key benefits of intermittent fasting is its capacity to stimulate autophagy, the brain's internal recycling and repair process. When energy is scarce, cells begin to clear out damaged organelles, misfolded proteins, and dysfunctional components. This is particularly important in neurons and glial cells, where the buildup of beta-amyloid, tau, and dysfunctional mitochondria contributes to cognitive decline and neurodegenerative diseases like Alzheimer's. There's growing evidence that intermittent fasting may enhance lysosomal function and upregulate autophagy-related genes, improving cellular housekeeping mechanisms in vulnerable brain regions. In doing so, fasting may help remove not only structural toxins, but also rebalance intracellular metabolism, including sugar utilization. In astrocytes, the brain's key regulators of glycogen storage, intermittent fasting appears to enhance metabolic flexibility. Normally, these glial cells store modest amounts of glycogen and break it down into lactate during periods of high neuronal activity or stress. However, in insulin-resistant or chronically overfed states, glycogen regulation can become impaired, leading to abnormal accumulation or sluggish turnover. Fasting periods may reactivate the pathways that govern efficient glycogen synthesis and breakdown, particularly through activation of AMP-activated protein kinase, EMPK, a sensor of cellular energy stress. EMPK promotes glucose uptake, fatty acid oxidation, and mitochondrial biogenesis, while suppressing anabolic processes that contribute to dysfunctional glycogen buildup. Another critical advantage of IF is its effect on brain insulin signaling. Intermittent fasting improves systemic insulin sensitivity, which may also extend to the brain. This is significant because insulin in the central nervous system plays a subtle but essential role in synaptic plasticity, learning, and memory. In states of insulin resistance, neurons may struggle to take up glucose or respond to trophic signals, effectively starving despite a glucose-rich environment. Improved insulin sensitivity through fasting could restore neuronal access to energy and support synaptic integrity, essentially resensitizing the brain to its own fuel system. Emerging studies in both animals and humans offer early but promising support for these effects. Rodents subjected to alternate-day fasting or time-restricted feeding protocols demonstrate increased expression of brain-derived neurotrophic factor, BDNF, improved mitochondrial function, and enhanced learning and memory. Human studies, though still limited, suggest that intermittent fasting may improve executive function, reduce markers of inflammation, and help normalize glucose metabolism in individuals at risk for cognitive decline. These benefits may be especially relevant during the preclinical stages of neurodegenerative disease, where subtle metabolic disturbances precede structural brain changes. However, caution is warranted. The effectiveness of intermittent fasting in resetting brain sugar metabolism likely depends on individual metabolic status, age, and underlying health conditions. For example, older adults, individuals with diabetes, or those with compromised glycogen storage capacity may require tailored fasting protocols to avoid hypoglycemia or cognitive fatigue during fasted states. The duration and frequency of fasting periods also matter. Too short and the metabolic switch may not occur, too long or too frequent, and it may trigger stress responses that outweigh the benefits. Furthermore, the benefits of IF are not purely a result of energy deprivation. The quality of food consumed during feeding windows plays a major role in determining outcomes. A fasting pattern followed by high-sugar, nutrient-poor meals may blunt or even reverse the metabolic gains. For fasting to truly reset brain sugar metabolism, it must be accompanied by dietary choices that support insulin sensitivity, mitochondrial health, and antioxidant defenses, such as whole foods rich in fiber, polyphenol, healthy fats, and plant-based compounds. In summary, intermittent fasting offers a compelling strategy for improving brain energy metabolism by reducing reliance on constant glucose intake, enhancing glycogen regulation, and activating stress-adaptive pathways like autophagy. These mechanisms collectively promote greater metabolic flexibility, improved neuronal resilience, and the potential reversal of early neurodegenerative processes. While more long-term human research is needed, the current evidence points to fasting not merely as a dietary strategy, but as a metabolic intervention with the power to recalibrate how the brain handles sugar and, in doing so, protect its function over time.